Now that we have the basic gas laws down and we know how to use PV equals nRT, the ideal gas law, to solve problems, now let's turn our attention to how we can use gases in reactions, how we can do stoichiometry. Well, if you think about what we've done up till now with stoichiometry, let me get a pen out here. What we've done is primarily we've said, okay, look, I understand that if I'm going to do stoichiometry, I need to have all of those units in moles. And quite often up to this point, we may have had mass amounts, say 2.56 grams of lead or something like that. And we know we'd have to do a gram to mole conversion first before we use it in a before and after table or any other stoichiometry strategy. If we had, say for instance, something that was aqueous, quite often they would give us the concentration of it. Let's say it was 4 molar, and we'd have to know the volume. Well, how many milliliters did they give us if it was a solution? And between those two things, we could also get to moles using molarity equals moles over liters. So we've had those two strategies, and the whole time the approach has been to get to moles, and then we could do our before and after work. Well, understand that it will also be true when we're dealing with gases that we will also have to get to moles. With gases, we may get into or out of our stoichiometry. Say, for instance, we had the number of moles of hydrogen made at the end. Well, if we wanted to know the pressure, volume, or temperature, we could use the ideal gas law to get those moles back to any of those other variables. The opposite is true too, right? Which is, instead of giving us grams, which we know we have to convert to moles, or concentration and volume, which we know we have to get to moles, it's possible that they may give us pressure, volume, and temperature, but we know we can use the ideal gas law to get to moles, and then we're ready to get into the stoichiometry. So the way I think about this is, if you're given pressure, volume, temperature at the beginning, you may need to pivnert your way to get to moles into the table, or you may need to pivnert your way out of the table. But it's the same concept as converting grams to moles or molarity and volume to moles. It's just a new way of doing it. So here it is. We've got a nice reaction. We've got hydrogen peroxide going to water and oxygen. Incidentally, if you didn't know this, hydrogen peroxide, this reaction occurs when you pour hydrogen peroxide on a cut when you're trying to sterilize the cut, because it decomposes to make oxygen gas, which is a strong oxidizer and kills all those bacteria. So that's what is going on there. But it does make a couple of gases here. Now let's look at the reaction and do the labeling together, and then you can solve it all on your own. So if you react 1.1 grams of hydrogen peroxide, so I'm going to say we've got 1.1 grams of this, what is the volume of O2? So clearly we want to know something about O2. We want to know the volume of O2 that would be produced if the temperature is 30 degrees and the pressure is 730. So that's not too bad. It looks to me like we have a way of getting into the table going from grams to moles. We're going to do all of our mole work, and then at the end we're going to use pivnert to get moles back to volume. Now if we're going to have moles somewhere in our table and we're going to get to volume, obviously we're going to have to know the pressure and temperature, and you can see that they give you that. So you know the temperature is 30 degrees. Got to be a little careful there though, right? And you know that the pressure is 730 torr. You got to be a little careful there as well. So I want you to start with your gram to mole conversion, solve it, and then we'll see if your answer is right. So the answer I got was 0.42 liters. Whoops, let me go back. Was 0.42 liters. If you got that answer and you feel like you know what you're doing, you can skip forward a little bit in the video until the next question. If you didn't get that answer, let's look at what you do here. So I converted grams of hydrogen peroxide to moles. I'm ballparking a little bit here, but you can see in the before column I get 0.0324 moles of that stuff. It is the limiting reagent because there's no other reactant, so I have 0 moles and it's going down by 2x, which means that tells me that my x value is 0.0324 divided by 2. I get 0.0162. Now, I don't care about this because they didn't ask me about that. This is a product. It starts at 0 moles. It goes up by x. X was 0.0162 moles. And now that I know how many moles I made of that, I know what that is, we know this is 0.0821. We know that the temperature is 303. Yeah, I think I used 303 there. Just making sure 303 Kelvin because I added the 273 to 30 degrees. And then lastly, for the pressure, I used, I converted the 730. I would show this work, right? Because this is math. I would show this work. I got 0.961 ATM, and that's what I used for the pressure. And then I just solved for V, and that's what I got. Now you guys know me by now, and you know that I'm working on the fly. The reason I'm trying to show you all those numbers is if I make a mistake, put the comment in the Edpuzzle. For this next one, I want you to draw the reaction first. So liquid acetone, that's its formula, is burned in the presence of air. Write the balanced reaction for the net ionic equation. And I'll give you a hint, it's a combustion reaction. So check your work down at the bottom. Being a combustion reaction, you should have acetone reacting with oxygen to make CO2 and water, because all combustion reactions make CO2 and water, and then you just had to balance it. Okay, so here's the problem. I'll let you read it, and I want you to make sure that you draw the reaction on your piece of paper and label where things go. Then solve the problem. So the answer I get is 0.0015 moles. I think 2 sig figs because of this, but we'll see as we work through it. Now, if you didn't get that, know that there are a couple of tricks with this problem. First of all, you need to figure out what the limiting reagent is, because you have amounts of both of the starting materials. In other words, you have 0.010 grams of this, which you clearly are going to have to convert to moles, but they also give you the pressure, which is 0.950 atm of oxygen, the volume of it, which is, I'm going to go ahead and switch it right now because we know we're going to need it in liters, and the temperature, which is 293 K, maybe 0.15 if you wanted to add that. So these three things are going to have to get to moles, and that has to get to moles. It is clearly a limiting reagent. Now I'll tell you right now, if you want to jump forward, this is the limiting reagent. Acetone was the limiting reagent. The other trick to this problem is, if you are wanting to just check your work, although I'll run through all of it, is they said what are the total number of moles of gas in the flask. Well, of course, this is a gas, so you need to know how many moles of that you have. That's a gas. Clearly, you're going to add those two together, but what's the other gas that's going to be left in there? The excess amount of oxygen, right? That was a gas, and there's going to be some excess amount when we get done doing our B and A table. So if that's enough, you could check your work, see if you get the answer, and move on. If you didn't, I'm going to walk through the whole thing right now. Okay, so I'm not going to show all this work because I think you already know how to do this, but you would, of course, want on a test to do that, to show your work. So my gram to mole conversion here, let's see, I've got it written down. When I converted my grams of acetone to moles, well, the molar mass I used was 58.08, and I got 1.72 times 10 to the minus fourth moles. That's supposed to be a 4 there, okay? For oxygen, I took P, V, and T, and I did a PV equals nRT bit of work to it. I've already converted them all to the appropriate units. Make sure that you did that. And then we're solving for N. So N is going to equal PV over RT. When I did that, I got, I'm hoping I didn't label my little postcard very well here, 118 moles. I believe that's what I have. Okay. Now, I told you I thought this was the limiting reagent, and it is. If you go down to 0 moles here, this goes down by X, this goes down by 4X, you will find that the amount of this stuff that you have left is 4.92 times 10 to the minus fourth. Now, you can see me doing this all by before and after tables, and it's because you guys are getting pretty good at algebra. But of course, if you're a train tracks person, you're just going to start with your mole amount here, convert it to using a mole ratio to oxygen, and that's the amount of oxygen that gets used, and then you just need to subtract it from this amount. Okay, so you should get that same amount. So this is going to be important because that is an amount of oxygen gas that's left. And over here, these are both products. You start with 0. This one's increasing because it's a product. That one's increasing because it's a product. And based on what our x value was over there, I got 5.16 times 10 to the minus 4th moles for both of these. 5.16 times 10 to the minus 4th moles. Now, those were gases that were products that will be floating around the flask. Of course, we have our excess reagent left over, and if you add those up, you should get the total number of moles. Now, this one is a problem from a previous book that we've had, so I'm not going to read it to you, but I want you to write the reaction down, label it well. Remember, you got to label what you have, and then solve the problem. They say the answer is 3.5 times 10 to the minus 9th grams of magnesium. So let's run through it. Okay, so they give me all these values about the oxygen. You can see I've already converted the torr to ATM, although of course show that work. You got to show that work. It's just I'm trying to cut to the chase here. You got to convert temperature to Kelvin, and all of these things had to do with the oxygen gas. While we're here, I want to point out this wording. The partial pressure of oxygen is this. Well, very often when they say that, they're just trying to say the oxygen, the pressure of the pure oxygen. If there were other gases in there, there might be partial pressure of nitrogen, partial pressure of argon, and they might add up to a total pressure. So this really doesn't have a lot of meaning at the moment if it threw you off. But in any case, I've labeled them. Now let's see what they want. They want to know what mass of magnesium will react according to the equation. So I'm trying to figure out what mass of magnesium will react. So I don't have to worry about the product at all. Then we just have to fill out our table or do our dimensional analysis. If you're a person who's doing that, you got to get this to moles, right? PV and T, you got to get it to moles using Pivnert. And then once you do that, whatever method is best for you to get over to magnesium works. When I do my PV equals nRT work, I am solving for moles. So moles is going to equal PV over RT. Make sure that we're using these values, and R is 0.0821. And this is the mole amount I get, 7.14 times 10 to the minus 11th. Okay, this is a reactant, so it's going down by X. And I know it's going to be completely consumed because we're trying to find out how much of this would be needed to be added to just completely consume it all. So this also is going to be going down to 0. And so what we're trying to do is figure out what that starting mole amount is, which is 1.4, I'm going to say 3 times 10 to the negative 10th. That's meant to be a 10 moles. Negative 10, and that's my mole amount, and then all I have to do is take my mole amount, come out, and convert that back to grams. Siri, what's the molar mass of magnesium?
The answer I find is 23.985 atomic mass units.
Thank you, Siri. All right. Do that, and hopefully when we multiply those together, we get the answer 3.5 times 10 to the minus 9th. Lastly, we should always check sig figs because textbooks aren't super reliable on sig figs. They went with 2. Remember, this has 2, but when you add 273 to it, you're adding, so you really get up to 3 sig figs there. That has 3 sig figs. That's probably the thing right there that's limiting it to 2 sig figs. So I think their answer is right. All right, let's go to our last one. Now on this last one, I don't have a lot to point out to you except for just some wording that I don't want you to worry too much about right at the moment. So they talk about there's a nice story behind the oxidation of glucose. It produces CO2. You know what? It looks like a combustion reaction to me, right? Sugar reacts with oxygen, makes CO2 and water. Did you guys know that our bodies are combustion engines? They literally are. We require oxygen to breathe, and we breathe out CO2 as a product, and of course sometimes we have to go to the bathroom, right? That's why we produce water. Yeah, we're combustion engines. Anyway, they say, look at this wording, calculate the volume of dry CO2. What the heck? I mean, if you're like, okay, I get it, I need to calculate the volume of this stuff. What is the dry CO2? Well, that's going to come up in our next little bit about Dalton's law of partial pressure. But for right now, you can take that wording kind of like the partial pressure I said earlier. It just means the pure CO2. In other words, this CO2 was generated with some water, and so there's water vapor in there too. And they're saying just what would be the volume of the pure CO2. So there's really nothing to worry about there at all. Now, label the rest of the reaction and then come back and see how you did. Okay, the answer I get, which I don't stand by because I'm doing it before I write it down, is 21.4 liters. Kind of an interesting number. In any case, so how did that come about? Well, let's look at this. So I've done some conversions already. You notice I would not get, even if I was right about this answer, which we'll see in a minute, I would not get any credit for this because look at this. I did a temperature conversion without showing it. I did a mole conversion without showing it, which incidentally, the molar mass I used on glucose was 180.16. 180.16. So that's how I got there. And let me do my reaction mapping. So they're saying they want me to figure out the volume of this gas that's made at a body temperature. The reason I'm going to write the temperature here, now you got to understand that this temperature would apply to everything in here, not just the CO2. But I just have a feeling that they want me to use the ideal gas law at the end, right? We're like pivnerding out from moles. So I'm going to write the gas quantities here. Let's see, 0.970. So this is an example of a problem. We're not pivnerding at the beginning, we're pivnerding at the end. And yes, if you're wondering, can you use pivnerd as a verb like that? Of course, obviously. So I think what we need to know here is if we know the moles of CO2, we can use PV equals nRT at the end to get our answer. So that seems like a good strategy. They're starting with 0.136 moles of this stuff. And this time, just to spread things out a little bit, we're not going to do a before and after table. And I know you're thinking that's because I didn't leave enough room here to do one. And that might be true, but also because we just want to spread it around a little bit. So we need a different color pen. We're going to say, okay, if I have 0.136 moles of glucose, C6H12O6, and I do a mole ratio of 1 mole of C6H12O6 to 6 moles of CO2, that will give me my moles of CO2, which I might still have. I don't know if I do. No, I don't. So I got to calculate it. So I got 0.136 times, not times 5, times 6. I get 0.816, I'm hoping, moles. Boy, I can't remember if that's right or not. Let's see. Yes, roughly that is right. Disregarding sig figs a little bit, but roughly that's right. So now I know the moles of CO2, which you'd get in your before and after table at the bottom. Now I need to take that mole amount, that's N, and so when I do PV equals nRT, since they want me to find the volume, I'm going to solve for volume, nRT over P. I know that R is 0.0821, N is my 0.816, T we said was 310, which I'm going to put a little period there because when I add 273 to that, it's going to give me 3 sig figs. And then my pressure, it is in the good units, that's right, so we don't even have to convert that. And I see 3 sig figs, 3 sig figs, 3 sig figs, so I'm going to report my answer to 3 sig figs, so I think I'm okay with this. Hopefully you can check my calculation, but I think that goes okay. All right, great job. So my summary for stoichiometry is label where the values go. Make sure you get into moles before you do any stoichiometry. Can't do grams, can't do concentrations, can't do volumes. And then everything after that is the same.